Hello, everybody. Thanks for joining another month here of our ClearCalcs Learn Hour, our ClearCalcs webinar. As you guys all know, you signed up for today's cold form steel webinar here, run by one of our resident experts, Benham. As typical fashion, we'll wait about a minute or two until the stragglers come in. Everybody's working on deadlines, as we know. So we'll give it about a minute. Feel free to use that chat area, the question area, to send through your name, your title, maybe where you're joining in from, so we can continue to expand this ClearCalcs community. And it's always great to see some familiar faces here. Jim, great to see you as always. Thanks for joining. And like I mentioned, just sit tight for a minute or so, and then we'll start the presentation and learn about some cold form steel on this beautiful Wednesday afternoon. Hey, Randy, thanks for joining. Hey, Soham, great to see you joining in here. Hope all is well with you. All right, good to see you as well, Mohammed. All right, so what we'll do, just for sake of time, because I know everybody's busy, we'll get into it. I'm sure there'll be more people joining in. But just to start this webinar here on cold form steel, as you guys know, today we're going to be talking about designing a cold form steel beam using AISI S100-2016. And then we're just going to understand the design process using the direct strength method. Then if we could, there we go. So today, just a quick outline of today's webinar. So we'll do a quick introduction, which I'm doing right now, then I'll also hand over to Benham. We're going to chat about how cold form steel CFS is unique. We're going to run through the design of a CFS beam with some other example calcs. And then, of course, as always, we'll have a question and answer period here. We'll touch on this in a few slides, but feel free to send through questions that you guys think of throughout the webinar. What we'll either do is I'll either rudely interrupt Benham to ask him the question, or we'll save them until a Q&A session and make sure we get to as many questions as we can get to. And then a quick intro. This might be the first time some of you guys are seeing Benham. So Benham is a structural engineering developer here at ClearCalcs. Joined us about a month or two ago. Time is flying, I forget.
3 months.
So 3 months already. So see, I already lost track of time. So master's in earthquake engineering and computational methods in engineering. Very smart guy, much smarter than I am. Academic and industrial experience, you guys can see there. So he was in the petrochemical industry for 4 years, and he is also a published researcher on different numerical simulations and structural engineering. So like I mentioned, very smart guy. We're glad to have him part of the team.
Engineers waste time every day.
So as you guys heard there, a beautiful Australian accent. I wish I had one of those myself. If you guys haven't watched that intro video on ClearCalcs, feel free to do so on our homepage at ClearCalcs. Most of you people joining today have an idea of what ClearCalcs is. You know, it gives you more accurate results, eliminates wasted time, and is cloud-based, so available everywhere. Of course, as always, if you guys have any questions on ClearCalcs in general, we're here to help, but we're going to focus on cold form steel, potentially how to do it in ClearCalcs today. And then at this point, I'm going to hand it over to Benham. And like I mentioned, feel free to send through your questions. But Benham, go ahead and take it away.
So thank you very much, Connor. And hello, everyone. It's a true pleasure to have you here. And so first, a brief introduction about today's webinar. We're going to talk about designing a cold form steel beam based on AISI S100-2016. And we have certain assumptions here that we will follow throughout the webinar. So we're going to strictly talk about C or Z sections, bent about their strong axis. We're not going to consider considerable holes on the cross section because that's going to require some extra checks, and that will be beyond the scope of this. webinars, and also we're going to concentrate on direct strength method with the assumption of using pre-qualified sections. So basically every standard section is pre-qualified, and the non-standard ones will have some additional checks. And detailing will be only broadly considered here. So as Connor mentioned, so everything will be shared. Don't worry about if you miss anything as I go. And two notes about this webinar. So all the material that you see here, except for one part that I have cited accordingly, is from the code. And even it is strictly based on code, it doesn't mean that we are intending to communicate any special knowledge, because we are not on the AISI committee. So the outline, I'm going to start with how CFS is unique. Actually, two aspects. What makes it interesting for the industry, and also what kind of challenges you might expect in designing in the design process of CFS. So for some of you who might have not had a prior experience in designing CFS structures, it's useful if we start with comparing CFS with some other popular construction material. So when you compare it with hot rolled steel, there are several advantages. First of all, it can be manufactured for relatively light loads, short spans, or even a combination of them, in which case it makes it really not economical to go for hot rolled steel. It has very good values for strength to weight ratio. That is a very important parameter in material engineering. And also the packaging and shipping can be done much more compactly. That saves the considerable costs. And also when it comes to the load carrying performance for both in plane and out of plane, actually perpendicular to the plane, you can expect good performance from this material. For example, when it acts as a shear diaphragm. When compared with timber and concrete, so first, as I said, it's a light material, and even though it is light, it gives very good values for strength and stiffness. So you can reduce the overall weight of the structure while having good values for its strength and stiffness. So fabrication, erection, and installation are done much more easily, and there are not going to be significant delays due to weather conditions. Also, there's no need for formwork, which is kind of a pain for concrete construction. And also the detailing can be done more precisely, and the quality of the material is much more homogeneous. Also, it is of note that even if you are constructing a structure out of wood, you can still replace some members one-on-one with CFS. So when considered as individual structural framing members, so I will talk about it later on, but there's a wide variety of section types available. But some of the more common ones are, as I have mentioned here, C sections, Z sections, I sections, and there's actually no limit about this. I'm going to talk about it later. So usually the depth is between 2 and 12 inches, and the thickness is between 48 thousandths to 1/4 of an inch. Although for specific applications, these values might vary considerably. And if you are working with CFS as primary framing members, the rule of thumb is that the limit is up to 6 stories. And also something that I have to note here, remember that what we are focusing on here are the open sections. So exclude the closed sections here, because that's not the focus of us using AISI S100-2016. So moving on to the challenges, probably the most important one, buckling. So as opposed to hot-rolled steel, buckling is a very important problem here for CFS. And most sections are considered to buckle before yielding. Also for bearing, or as it is more preferred in the context of CFS, web crippling, it's really easy that it will control your design. So you have to be careful about buckling of the web, either at the bottom of supports or on the point loads, at the location of point loads. And so you're going to need, you probably need to use finite strip analysis, although there might be some other ways to bypass that. And also it needs to be done only once a section. And also the ability of CFS to be customized. So it's really strong, and the design methodology will stay consistent for any arbitrary cross section that you will use. So if you remember the good old categorization from hot rolled steel, compact, non-compact, or slender sections. So you might remember that the slender checks really control the the slender checks might be for only one category of hot rolled steel sections, and most of the sections are compact. But here for CFS, slender always is controlling, and you have to check it anyway. And there are three buckling modes. So local, distortional, or global buckling. So the image that you can see here from left to right, I'm going to talk about it later on in more details. And also, of course, you can go for stiffeners as a countermeasure to reduce the effect of buckling. So and also it's useful to know that so for example in cold form steel, these lips that you see here, so these divots, they actually perform as stiffeners. So one example of how cold form steel is different than hot rolled steel. Okay, so about web crippling. If the web isn't directly restrained either at supports or at the location of point loads, you have to check web crippling. And it, as I said, it's really likely to control the design. So for hot rolled steel, it's really rare that you have to go for them. The possibility of this part to control your design, but in CFS it's much more likely, and it's really dependent on the accurate definition of the cross section and how the loads are arranged. So finite strip analysis. I'm not going to go into details because we don't have that much time for it, but just some important points. So it's the preferred method in AISI S100-2016 because it actually requires you to do some sort of a rational analysis, and it mainly takes the form of finite strip method. So you generally have to do it once for a section, and of course, as I said, there are alternative methods. So about the figure that you see here, I'm going to talk about it later on in another slide. It doesn't hurt if I emphasize how customizable CFS is. So although you have access to more than 700 options from SFIA and SSMA, but still you can go for any arbitrary shape of the section and then analyze it and design it based on the clauses in the code, and it might turn out really economical for your project. So designing a CFS beam. So I don't think it's useful if I go into the details of every parameter in every equation. But something that I'm going to do is talk about what kind of things you have to be careful when you're designing a CFS beam. And I'm going to do it for the 5 different capacities. Five different types of calculating the capacities: flexural, shear, bearing, load interactions, and deflection. So starting, but before that, of course, so as you are aware, so that we have to calculate the demands based on ASCE 7 or the International Building Code. And then we have to move on to checking the limited states. So flexural capacity should be controlled either for positive moment at mid-spans or negative moments at supports. We're going to have to check shear capacity, web crippling capacity. Load interaction is divided into flexural plus shear buckling and flexural plus web crippling. And of course, we have to check for the deflections. So as I mentioned, there are 3 different modes of buckling that we consider: global, lateral, and distortional. So for each of them, we calculate the bending capacity individually. And to start with global buckling, so the definition based on the picture, based on the image that you see here, so the corners of the section will start to move, and you have to calculate M&E, which is capped by My. So for that, we need 2 elastic moduli. One of them, SF, is the extreme compression fiber related to extreme compression fiber, and the other is relative to the first yield fiber. So conservatively, you can go always with this, but if you want some more capacity, you can calculate SF. And although they are usually the same, but if the section is bent around an axis with asymmetry, so for example, if you bend a C section about its weak axis, then they will differ. And so Fn is the global buckling, is for global buckling. And although you have equations here, analytical ones here, you can also go for finite strip analysis or effective widths method. The main parameter that we work with here is the critical global buckling, the FCRE, and it depends on the type of the section. So I have brought here the equations for C section and Z section. So it's funny to note that Z section is exactly half the value of C section. And so some parameters here are geometrically derived. That aside, I'm going to talk about the other parameters here. So CB, it accounts for the pattern of the moments along each of the spans of the beam. And you can conservatively take it equal to 1. And sigma EY and sigma T, they are the lateral buckling stress and the distortional buckling stress. Of course, there's inelastic reserve. So given that it's not going to affect the stability of the structure, you can take into account a slight increase in the capacity, and based on localized yielding. And for that, there is a condition to be met. And if this condition is present, then you can calculate MP, the member plastic moment, and based on that, calculate a higher value for M&E. And although critical capacities generally don't depend upon the links, they might be for really short beams. I don't know, for example, less than 24 inches. And okay, so getting to finite strip analysis in more details. I know it might look kind of scary, but fear not. We have only two takeaway lessons from this. So the first one is you have to remember that the output of finite strip analysis looks like this. So it gives you the half wavelengths against load factor. And what happens is, okay, so I'm going to give it with an example like this. So imagine this is a beam, and I just bend it with two supports at the ends. So you can see that the whole length bends, but imagine that the whole length is restrained, and then I start bending it. So the wavelength is considerably shorter. So that is what happens here as well. So actually, finite strip analysis sees through every possible half wavelengths that can happen and every possible divot, and then it gives you two local minima, which correspond to the local buckling capacity and the distortional buckling capacity. So if I want to take these to the equations, which we will see in the next slides. So starting with local buckling, which happens when the corners of the section remain still, but the flat portions start to bend. So we consider an interaction with global buckling, and that reflects when we use MNE here in calculation of the slenderness coefficient. The half wavelengths, referring to the image that I showed you in the previous slide here. So it's usually about 4 to 10 inches. And so again, we can go for some extra capacity using inelastic reserve. Although it's definitely important that two conditions are met here and here. So these conditions translate to the fact that global buckling will occur after yielding, and the local buckling will not control the design. Based on that, we check the region of first yield, and whether it's compression or in tension. Then we have the relative equations to calculate M and L. So similarly for distortional buckling, although here you have to consider that the distortional buckling happens when corners of the section start to move, but not all of them at once. So that's the definition. And it does not consider an interaction with global buckling. That is reflected in this equation when we use My instead of MNE. And it usually occurs with a half wavelength about 16 to 30 inches. So similarly to the previous ones, we can use additional capacity using inelastic reserve. And again, it depends on which region the first yield will occur. So overall, we will find the value of the max, the minimum among MNO, MND, and MNE, local, distortional, and global buckling, and we multiply it by PV, which always equals 0.9. So moving on to shear buckling. So here we the good news is that we only work with analytical methods. And so the equation is kind of straightforward. So the only thing that I think is good to remember here is that the critical shear buckling capacity is comparable to go from flexural capacities. But you just have to remember that we have either unreinforced webs or reinforced webs. And in the case of reinforced webs, it also relates to the geometry of the shear panel. So based on the location of shear stiffeners, we will have a width and the length of the shear panel, and then we can check it to calculate the corresponding value. So without the stiffeners, we calculate Vy, yield shear force of cross section, And we also calculate the slenderness ratio coefficient based on Vy and VCR from the previous slides. And based on that, we either have the full value of yield shear force or a portion of it. And then the calculated value for Vn is multiplied by phi V equal to 0.95. Similarly, for the case of using the stiffeners, just remember that if the distance between shear stiffeners is more than 2 times the depth of the beam, then it's considered to be unstiffened. Also, if you note, it's actually identical to flexural local buckling, because what happens here is that you're actually considering the local buckling in the shear panels, and that's why the equations are identical, are essentially identical. And again, it's multiplied by 0.95. And so for web prickling, it all boils down to one equation. I'm not going to go again through all the geometrical geometry-related parameters. The important thing that I want to talk about here is the CX coefficient, so CR, CN, CH. So they are defined based on different tables and different types of section. And it's important to remember that these calculations, P of N, is calculated for each web. So if you have 2 webs for the cross section, then Pn has to be multiplied by 2. And also the reduction factors, they also should be looked up in the tables. So this is how the table looks like. Let's go through the terminology. So fastened or unfastened, it actually means bolted or screwed. And stiffened or unstiffened, it actually means whether or not there's a lip on the cross section. And 1 flange or 2 flange loading. So here in this image, if the distance between the 2 point loads is less than 1.5 the depth of the beam, then it's considered 2 flange loading, otherwise it's 1 flange loading. And for end versus interior, so if the distance between the point load and the support is less than 1.5 times the depth, then it's end, otherwise it's interior. Similarly for Z sections, but please have in mind that not all cases are reflected in the table. For example, if you have a fastened beam but with unstiffened flanges, we don't have a corresponding case here. For that, you have to go for the more conservative case and take the conservative values. So load infractions, so there's actually not much to be said here. I think just the important part is to remember that it depends on the existence of shear stiffeners. So with shear stiffeners, you just have to go for the square root of the sum of the squares. And with shear stiffeners, you have to check two new values, MALO and VA, which are basically considered as local buckling, but without global considerations. So these are actually the non-reduced values for flexural and shear capacities. And of course, you have to calculate it, MALO and the VA, and then plug in the values in the related equations. So for flexure and web crippling, it should be considered for both supports and point loads. And the phi value here is not considered individually; they are both together. And we consider 0.9 for both of them. Again, it depends on the reinforcement of on the different cases that we might use. For example, for unreinforced single webs or back-to-back C sections or nested C sections or other types, that you might come across in the standard. So they each have different equations. And of course, there are some exceptions or special cases that you might find useful. So deflection, I think the most important part here, the most important point is that you have to remember about the effective moment of inertia. So there are three cases that you can, three different methods that you can use. You can either conservatively use the values given by the manufacturers, or you can go for some long equations given in the design manuals, or something that is not that conservative. You can use this equation, which actually multiplies the gross moment of inertia with the ratio between demand to capacity at service loads. And manufacturers usually consider this the M value for a reasonable combination of dead load plus live load. And of course, have in mind that the value of E is slightly boosted because of the cold formed processes. So one final point, because we actually talked about the general requirements for cold formed steel beams, just it's probably useful to keep in mind that for some special cases, you can go for the specific standards and specifications, which probably give you some more capacity. For example, for diaphragm systems, which you can refer to AISI S100-2016. All right, so moving on to examples. I'm gonna start two examples.
Hey, Benham, can I just interrupt for 1 sec? I got a question from Trent, which was a great question. So in your slides, on page 31 or slide 31, it mentioned fastened versus unfastened connections. He was just asking, does fastened mean like bolted or screwed, and unfastened means there's no connectors? Or he was just wondering if we could expand on that a little bit more.
Yeah, so as much as I know, fastened means bolted and unfastened means screwed. But if necessary, I can go double check. But as much as I have been dealing with this, I think so. Fastened corresponds to the case of the bolted to the supports, and unfastened means screwed.
Perfect. Thank you, Benham. And then what we'll do as well, Trent, as I'm sure many of you know, so Brooks, who is our head engineer, specializes in cold form steel. So anything that we might be a little unsure of, we'll just make sure to run past Brooks, and then we'll send you guys some responses and follow-up emails. But I appreciate that question, Trent, and thanks for the response, Benham.
Definitely. So yeah, we're going to double check that with Brooks, definitely. And yeah, so as much as I know, it relates to the fastened or unfastened based on bolted or screwed. Yeah. Okay. So any other question, or should I move on to examples?
Nope, that's all for now. You can jump right into examples.
Okay.
Thanks, and sorry for interrupting there.
No problem at all. Okay, so so I've prepared some examples here, but probably doesn't hurt if I start from scratch for those of you who have not worked with ClearCalcs before. So I can create a new project here. So let's name it webinar CFS, and then you can use the different unit systems, and anyway, so add a calculation and then cold form steel beam, and of course I can again here use generate beam. So let's do the design example that I had with each other step by step. So we have, for the example, so a 68 inches beam. So the total length is simply supported, and it's considered for office building floor purlin, and the tributary width is considered to be 16 inches. No transfer shear reinforcement, and the laterally unbraced length is considered braced length is considered to be 24 inches. Laterally unbraced at 24 inches, and also torsionally unbraced for the whole span. And so if we want to do it step by step in ClearCalcs, so first, the whole length. So here you can actually use feet, but it's also doable like this. So you can do it like this. If you have with feet and inches, then it'll do the trick. And okay, so the unbraced length is considered 24 lateral, okay, and the torsional bracing and bottom flange unbraced for the whole length. And so the section that we were going to consider is this. So basically, these three numbers here. Sorry, just a second. All right. So okay, so these three numbers, they correspond to the height of the section. Then S corresponds to C section actually, and there's Z, there's T, so on and so forth. And the other three numbers are for the widths, and 54 is about the it shows you the thickness of the section, and there's also an index for the strength of the section. So 362S, and I'm gonna use the same here. Okay, so as I said, we have a very large library of sections, and it'll definitely help you a lot. And it's really easy and straightforward to use it. So I'm gonna just type in. No, sorry, 362S 1, and then 37, and okay. So this was the section that we were going to use. And moving on, so it's pinned restraint at both ends, and the dead load and the live load. So I'm gonna fix it as at 15 here. And so with that, now there's also other options for introducing the loads. But for this, so actually there's a rich amount of options and features that you can work with on ClearCalcs. So as you can see, the design criteria and the deflections, and load combination analysis, and so let's consider the local buckling. So you can check these here, and for different modes of buckling, and shear capacity, actually everything that I have talked so far, so you can see it here. And so web crippling, and overall you will have the light checks here. So as you can see, it passes, and I have every information that I need about the capacities and the demands here, and the distribution of moment, shear, so on and so forth. So also it's useful to know that, as I said, so you can easily see if there's a more economical section here. So you can see which sections pass which sections don't pass, and how the demand to capacity ratios vary among these. Okay, so for the next example, again, I'm going to go for generic beam. So this one is a little bit more complicated. So as you can see here, we have 3 supports and the loading at the whole span. So the bracing conditions will vary here as well. But we're going to do it step by step. Okay, so I'm going to start with, I'm going to check the section later on, but for the whole length, actually, you can do it like this. So if you go to the image, you can see that 72, 120, and then 24. So for avoiding any kind of mistakes, I'll just do this. 18 feet, and then so we had the these ones to be we consider these ones to be 48, and then we have to add the information about the location of the supports. So we had one of them at 72. So it has to be feet. Then I'm going to do it like this. And then the other one, 72 plus 120. And yeah, so that's it. And bearing lengths, distance to web hole, and yeah. So now, as you can see, for this one, I think, yeah, here I have to change the loading as well, although it's not that important. So as you can see, this one does not pass, and the problem is for deflection. So yes, I have to put in the considered section type as well. So S100-62. I'm going to check it for S, and then 54. Okay, so as you can see, this one does not pass, and it's slightly, but the deflection is exceeding the allowed value. But so one choice would be for choosing different sections. But imagine a case that that you need back-to-back sections. So we have added that feature as well. It's quite practical, and so actually, when you imagine a case where web crippling is controlling your design, in that case, it's the most economical. Actually, the smartest solution would be going for nested Z sections or back-to-back C sections, and we offer that possibility as well. So and that should be about the design examples. And yeah, so about conclusion quickly, because I think I kind of exceeded my amount allowed time. So we talked about why CFS is unique. We talked about the issue of buckling, why web crippling is likely to control the design. We talked about finite strip analysis and how it might be used, how it might be needed in the design, and how highly customizable CFS section types are. Then we talked about the beam design checks for different capacities, flexure in global, local, and distortional buckling capacities, and of course using finite strip method. Then we talked about a shear yield and shear buckling which was mainly defined based on the existence of stiffeners. And we talked about bearing or web rappelling, the tables, the large tables that we talked about, the terminology that you need to know about those tables. And of course, load interaction, the case of flexure plus shear, and the case of flexure plus web rappelling. And also the deflection, which, as I said, the most important part is considering the effective second moment of area or moment of inertia. So yeah, and we also did some examples. So that sums the webinar up. And please let me know if there are any questions. Hopefully I can help.
All right, thank you, Benham, for running through that, running through all the math, and then running through a couple examples specifically related to ClearCalcs. For everybody's knowledge, so right now we'll just run through any questions. Feel free to use the question and chat box to send through those, and we'll get to as many as we can. We do have another one from Trent Larson here. Thanks for sending this through Trent. He was just wondering if you would be able to touch on the difference between a nested connection versus doubled for a cold form steel beam. Would you be able to provide any knowledge on that, Benham?
So nested supports or nested sections?
So nested section. Sorry, I was just reading
Yeah.
just verbatim from the question.
Yeah, I see. So honestly, I think that's better to be answered by the expert, because I probably don't have any specific insight into that. But yeah, so I'm going to keep taking note of that one. So the question is how a nested Z section differs with back-to-back C sections.
Yeah, so what I'll do, and thanks again for sending that through, Trent. I made a note of this question here, as well as just confirming the fastened and unfastened connections. And we'll just double check with Brooks later today and go ahead and send out an email to all attendees. So that way, when you guys are watching this and when you guys are kind of having some coffee later, thinking about this webinar, we'll be able to send you guys some responses and make sure we're all on the same page. So great question again there, Trent.
Yeah, thank you.
And then thanks, Chris, for sending through some compliments there. We do have another question from earlier. There's not too many questions flooding through here. So again, if anybody has any, send them through. But Trent did have another question regarding built up sections in ClearCalcs. So one thing I do want to point out to everybody that's still online here, Benham, if you would be able to go back into ClearCalcs here and just quickly point out, we don't need to necessarily run through an example or anything like that, but I just want to make sure everybody knows how to locate these. In ClearCalcs, if we're looking at built up sections, so if you can just click on the green add new calculation there on the left, and then just scroll down a little bit.
Oh, okay.
So just for everybody's knowledge, what we have here in these cross sections, yep, you know where I'm going. We have a custom cross section properties analysis tool and a custom thin walled section properties tool here. So just for everybody's reference, if you do have a more built up section with hot rolled steel or more standard steel, feel free to use the custom cross section properties one. As always within ClearCalcs, we're always improving, adding different features. And as always here as well, these are just different common presets to help you guys along. You could just go with a generic custom section to kind of start from scratch for a composite steel section there. Similarly with the custom thin walled sections, that will be more focused around today's discussion. We're looking at more cold form steel and light gauge steel. So just wanted to point that out. And thanks for that question earlier in the webinar, Trent.
one thing to add there. So about the custom sections, as Connor mentioned, so we do have this feature here, but just please note that connecting the design of custom sections, sorry, the analysis of design sections to the design is still in a work in progress. So correct me if I'm wrong, Connor, because last time I checked, our team is still working on the full design process of custom sections. But indeed, you can define any type of cross sections here with arbitrary material properties and then analyze the beam.
You're exactly correct there. Exactly right. I'd say the last little tip and trick there is you guys, again, the big difference, like Benham just mentioned, between analysis and design here at ClearCalcs. You can then use the beam analysis calculator to analyze that section that you built up. But yes, we're still working on getting that full design, kind of closing the loop there on those custom sections. And then just touching on a question here. Thanks, Jason, for sending through that question regarding, so this was another question regarding the nested and double. So Jason, we're gonna double check there with Brooks just to make sure we're chatting with our resident expert, and we'll send you guys a response via email, everybody who attended this webinar, regarding the nested versus double at interior support. So thanks for sending through that question there. And then no more questions as of now. Of course, Benham and I will hang for about another minute or two. If nobody has any more questions, I know everybody who's attending this webinar is busy, has some work they got to do. So if you do want to jump out and kind of either grab lunch or start working on some other projects, feel free to do so. Thanks everybody as always for joining. You should be receiving, everybody should be receiving an email. One, as a follow-up to this. Two, as our next webinar that's coming up in October. I believe, don't quote me on this, but we're going to be focusing on some tips and tricks and time-saving tools within ClearCalcs. So a more general kind of things that our most successful users use, but some people might not be finding as easily. So we'll make sure to point those out and help you guys save even more time within ClearCalcs. So thank you all again for joining. So like I mentioned, Benham and I will hang around for another minute, but feel free to head out and enjoy the rest of your day, everybody. All right. It looks like people are trickling away here. Thank you, everybody. And then Trent, thanks for this additional question here regarding fastener checks for cold form steel. So I'd say with connectors, fasteners, everything like that in general, we are constantly adding and improving. As you might have noticed, we added a wood connections based on the Simpson Strong Tie database a few months back. The cold form steel, if you ever ask us if we have any plans of adding something, the answer will be yes. It'll just be a matter of timing and how near into the future we're going to add it. So let me double check with the team on priorities and where that's going to be sitting in the roadmap. Likely not a near future add for fastener checks for cold form steel, but definitely something that will be in there eventually, as we do want to be that one-stop shop. And then Jason, this question about steel I-beam. So if you'd be able to expand on that a little more, I'm gonna infer it has to do with the connections and fasteners that I was just talking about for the more hot rolled steel. Again, I'd say the hot rolled steel connections might be sooner added to ClearCalcs than the cold form steel, but I'll need to double check with the Eng team on our roadmap there. Yep, so any connection design for steel I-beams. Yeah, so if you guys notice, as I always point out, just to make sure you guys know we're not BSing you, if you look at the Australian calculator database, we do have steel to steel, wood to steel, wood to wood, welding connections, so all different types of connections. So we will be adding both hot rolled steel and cold form steel connections to ClearCalcs. It's just a matter of when those will be added. So thanks for sending those questions through, both Jason and Trent. And then appreciate Mohammed, Robert, Colton, Soham for the kind words there. Appreciate it. And there's no more questions coming through. It seems like quite a few people are trickling out here. So for the sake of time, what I'll go ahead and do is we'll end this webinar here. As always, you guys know, use that blue help button in the bottom right-hand corner to reach out to us. You could reach our structural engineer who's on support duty for the day. I get those as well as our director of customer success to help you guys be successful in ClearCalcs. Again, thank you all for joining. Enjoy the rest of your day. Good luck with those deadlines, and we'll see you guys next month. Thanks again, Benham.
Thank you so much, Connor, and thank you everyone for joining us today.
See you, everybody.